Section 2.2 is on page 104. Talks about the inverse of a matrix. The section all is wrapped around the inverse. Not that long of a section, but important. So we start by saying we have, if you have a square matrix, we say that's invertible if there is a matrix C, so that if we take C times matrix A and A times matrix C, we get the identity matrix. So basically, if you're saying it's invertible, you're saying there is an inverse. This unique inverse is denoted normally by A to the negative 1, in which you take A inverse times A and A times A inverse, and you should get the identity matrix always. Keep in mind, it has to be a square matrix. And then a matrix that is not invertible is called a singular matrix. And an invertible matrix is called non-singular. I suggest you stick with invertible and stick with singular. Don't try to memorize both, it's kind of confusing. So if it's not invertible, it's singular. Think of singularity, right? Like a black hole. Doesn't exist. So not invertible. Theorem. If you have a 2 by 2, we have a shortcut for a 2 by 2. I'm going to show you how to find the inverse of anything. But if you have a 2 by 2, first you take A times D minus B times C. If that doesn't equal 0 for a 2 by 2, automatically A is invertible, and there's the inverse. It's 1 over, this is called the determinant. That's coming up in a section by itself. And what you do, you swap those, and you multiply those by a negative. And if the determinant equals 0, this is not invertible, or it is a singular matrix. Now there's another way of doing this, but for a 2 by 2, this turns out to be very quick. The alternative to finding an inverse is for you to write A and the identity associated with A. Use row reduction. When you get I on the left hand side, whatever's on the right hand side is the inverse. That's a lot of work. Instead, we look at this, call this A. So this is on page, let me just get the page really quick. That's on page 116, I believe. 111. So first I'll find the determinant of this. Again, I know we didn't define that yet. Call this the matrix A. Determinant of A is 12 minus 14, which is a negative 2. That's very good. Which means I could find, if you call this A, I could say the inverse of A is 1 over the determinant. And what I do, I switch the diagonal terms, and I multiply the non-diagonal terms by a negative. And there it is. So the inverse here is actually negative 2, 1, 7 halves, negative 3 halves. And that takes care of it. And if I wanted to do here, again, if I call this A, I'll find the determinant of A, and that will be negative 24 minus a negative 28. So that's a positive, that's a 4. So the inverse of A would be, 1 over 4 times, you switch the diagonal entries and you multiply the non-diagonal by a negative. That makes this a negative 2, a 1, a negative 7/4, and a 3/4. Finding the inverse is a lot of work. We're more interested in this class, what does that mean and how do you play with that. We have a theorem, and I need to elaborate on the theorem a bit. So theorem 5 says if A is invertible n by n matrix, and you have the equation A x equal B, what you do, you multiply on the left by the inverse. This gives you the identity matrix. And the identity matrix times any matrix is the matrix, kind of like 1 in real numbers. And that's how you get the solution. So this process is important in this class, a lot more than we like. I would like to take an example. I'm going to take problem number 4, and I'm going to say, suppose you have the equation 3x minus 4y equal a 1 and 7x minus 8y equal a 2. The process is extremely important. I can write this as a matrix equation. I could say that is 3, negative 4, 7, negative 8 multiplied by xy equals, I'll leave space, 1, 2. But I already figured out what the inverse is. If I multiply on the left hand side with the inverse, if I multiply with a negative 2, 1, negative 7 fourth, 3 fourth, if I multiply those, guess what I'm going to get? The identity matrix. The identity matrix for a 2 by 2 is 1, 0, 0, 1. It's always 1 across the diagonals and 0 everywhere else. If I multiply what's on the left, that's 2 by 2, that's 2 by 1. That'll be negative 2 plus 2, which is a 0, and negative 7 fourth plus 6 fourth, which is a negative 1 over 4. And we know that the identity times any matrix is the matrix, in this case the vector, and that's how I find the solution. I'll say the solution to this system is 0, negative 1. So this is the idea. So again, let's get this identity matrix out of the way. If you want to, the inverse out of the way, if you want to find the inverse of A, you write matrix A, augmented, the I identity matrix. Remember, it has to be an n by n. And you do row operations to get the identity on the left, and the matrix on the right will be the inverse. I'm going to demonstrate that with 2 problems. So the way it works, if I am to make this 1, 0, 0, 1, the goal is to make this the identity. And we already did that. We want to make this a 0. How do you do that? You multiply row 1 by negative 4, row 2 by a 5. You add them, put the result in row 2. So the process is a bit tedious. You want to work slowly, because the chances of making a mistake is very high. So the first row, I will divide at the end. That's easier. Multiply by the top by a negative 4, negative 20, negative 40, a negative 4, and a 0. The bottom by 5, 20, 35, 0, and a 5. Add those. That's a 0. That's a negative 5. That is a negative 4, and that's a 5. Now, I'm going to use this bottom row to make that a 0. I'm going to take, again, twice. I'm going to take twice row 2 plus row 1, put the result in row 1. So if I multiply bottom row by 2, 0 plus 5 is 5, negative 10 plus 10 is 0, negative 8 plus 1 is negative 7, and 10 plus 0 is 10. And now all what I have to do is take row 1 divided by 5, put it back in row 1, take row 2 divided by negative 5, put it back in row 2, and I'll get 1, 0, negative 7 fifths, and a 2, and 0, 1, 4 fifths, and a negative 1. And if this is A, the inverse of A would be negative 7 fifths, 2, 4 fifths, negative 1. It's a lot easier to take 1 over the determinant for a 2 by 2, but for a 3 by 3, that's not possible. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Again, the identity matrix across the diagonal. I want this to line up nicer. So my first step, I'm going to make this a 0 and this a 0. I'm going to take 4 times row 1 negative plus row 2, put the result in row 2. And I'm going to take twice row 1 plus row 2, 3, put the result in row 3, and this is what's going to happen. row 1 unused, unchanged. Multiply by negative 4, that's a 0. Negative 4, that's 8, that's a 1. Negative 4 plus 3 is a negative 1. Negative 4 plus 0 is a negative 4, a 1, and a 0. If I multiply by a 2, 2 plus 2 is 0. Negative 4 plus 6 is a 2. 2 minus 4 is a negative 2. Negative 2 plus 0 is a negative 2. 0 and a 1. Now I'm going to use those two rows to make that a 0. I'm going to take twice row 2 I just rearranged the furniture a bit. Not to worry, I didn't change anything. So now, like we were saying, if I take twice, if I take negative twice row 2 plus row 3, put the result in row 3, I will get and multiply by negative 2, that's a 0 plus 0, 0. Negative 2 plus 2 is 0. 2, plus 0 is 2. Oh yeah. Okay. Negative 8 minus 2 is a 6. That's a negative 2, and that's a 1, so this is not possible. Why? Because it's a singular matrix. So if one of those zero out, there's no way of making that a 1 after that. Which means there's no way that could happen. So this is not possible. You would say this matrix is not invertible. And the homework is right there. Okay. Patient. There we go. That concludes this section.